Okay. Um, Hello, everyone. Welcome to week three. And today we are working on the challenge of creating a AI model to predict who will survive on the passage of the Titanic. And so this comes from uh, a, a project, a challenge on Kaggle, and this is the challenge page, and it's called Machine Learning from Disaster. And to get started, all you have to do is sign into Kaggle, and then uh, download these two files, the train and the test set, and that includes information about um, all of the passengers here on the ship, their sex, age, ticket, cabin, and all this information about them. And your job is to make a model and hopefully to join this leaderboard of people who've created all sorts of different models predicting who survives and who drowns. And this is verified with real data of actual passengers who went on the Titanic. So it's a cool challenge. And yeah, I will let Burhan continue for the rest of this workshop.
Right, sweet. So, I've already constructed a machine learning model that does this job, and we have presented that in the previous class. But let's just start with the Excel, and then we can move towards the code. So, hmm. Yeah, I hope this is visible to you guys.
Yeah, I'll throw it up there. And Felix, if you want to go ahead and like download that data set while we're doing this, that's also probably
All
helpful
right.
for you.
So,
Yep.
like, we have like three files given by Kaggle, which is one's the training file, the other one is testing, and the third one is like the format in which you have to submit in Kaggle. So, we have the passenger ID, we have survive, we have the class like first class, second class, third class. We have their names, we have their gender, and then we have their age. You would notice something that we have like some the data is missing, which is unusual for us because previously we were encountering this sort of problem. So we have to come up with something which would actually enable us to either fill this data, or we could just skip this whole row if necessary. But like what I have done in the Colab code, that I have actually took the mean out of mean value of all throughout the column, and then filled each of this based on it. So that's one of the strategy we can use, but there are different ways that you can counter this by using feature engineering. But I took the simplest way, which was taking the mean of the ages. And the other thing you would notice is that we have like gender as male and female. So we have to convert that in float in order to like uh, train the model. So that's one task. We have to fill the incomplete values, and we have also missing values in embarked. It's like I don't think we have much values that are missing in embarked, but we still have like a few. um, yeah, we'll have a look at the code, so it's actually better for us to visualize how the data actually looks like at the moment. So yeah, that's the code. We got the libraries and stuff, and then we imported the library and we read the file. We could see that the columns with missing values is age, that has 177 missing values. Cabin. Now cabin is actually this column. So we have like now much data here, and I personally dropped this column just because we only have like 5 or 6 filled values, and the rest of them are missing. So I decided to dodge it completely instead of like filling it. So we had cabin, and we have two missing values in embark. So this just gives us sort of idea that how the data currently looks like raw. And then we actually took the mean of the column, and for the age one, and then we filled it with the mean values. And then for the other column, which was embarked, we actually filled it. We actually took the most frequent one, out of the whole column and then filled it as well. So this sort of gives us an idea that after doing this data manipulation, we have like we have no missing values left. Considering we're not talking about the K-bin one because I ignored it, and then we were supposed to encode the values because the gender was in objects. So string data type, and then we converted it into float, which you could see is male is 1 and the female is 0. And for embark is like other we have like different variables for embark. We have S, C, Q, which is like the place that they started their journey from. So Southampton and two more cities, I guess. And then they we have encoded that. And then so now that we have all the integer and float values, we could actually construct a heap map to see what the data actually looks like. So we're trying to predict if the person survives or not, right? So we have to look in this row, and we could see that we have highly negative correlations with the gender, and we have 0.26 with the fare. So it does make sense because if you pay more, you get a better cabin, and that just results in the chances of you surviving more. So that could be a case, and then we have highly negative correlations as well. This was just to get a sort of idea on what the data actually is telling us at the moment, and then
Felix, do
we
you have any
actually.
questions? Felix and Nishant, do you have any questions so far? Does that make sense? Okay.
So far makes sense. I'm just curious how you choose the variables now, because there also could be some kind of variables affecting each other, right? It doesn't like this graphic doesn't show you everything probably, but yeah, just I'm just curious. I'll be patient.
Right.
Yeah,
So
just
yeah,
a quick comment, Brian, before you proceed. For the data imputation, so in one place you have done this mean imputation, and then in a second place you have done the mode imputation. So we usually do mean imputation in places where the values are missing at random. So there is not a like a big chunk of data missing. Consecutive values are missing. We don't do it there. We usually do it when we have missing values that are at random. So in those places, mean imputation is a better strategy, and the mode imputation is usually better in whenever you are doing if the feature is categorical, so the values are categories, they are not some continuous values. In that place we usually do the mode imputation. And usually if there's a value that is occurring, like most of the time it's occurring throughout, in that place mode imputation would be a good strategy. So this was just a quick comment. You can proceed, Rohan.
thank you. So like we got the heap map to sort of like this was just to get the gist of it. You're right. It doesn't show you everything, but it does give you an idea. So yeah, we use the heap map, and then we have the data preparation. We dropped the columns which were like irrelevant to us because passenger ID was like just serial numbers starting from 1 to I guess we have like wait, how much entries do we have? We have like a good amount of entries. We have like 891, so it just starts from 1 to 891, and it doesn't really affect the data. And then we're obviously dropping the survived one because that's where we're gonna predict. And then we drop the ticket, we drop the name, and then I dropped the cabin as I told you guys earlier that most of the values were missing, so I dropped it. And then we have, yeah, we're trying to predict survive, so y is basically the survive, and this is what the x looks like for now. uh, we have the encoded values instead of the raw values. I dropped it right here just so you guys know. And then we're trying to use the scaler to transform the data further before we actually train the model. And then after using the min max scaler, and we have the exome. I personally didn't use this scaler previously, but Naveed and James told me to use it, and then we
Yeah.
split the
So
data. Yeah, yeah, go on.
just a quick comment. So you have used this min max scaler. Another one that could have been used here is the standard scaler. Both
Yeah,
kind of do the same thing. So when you have multiple features, if you remember, we discussed this that some of the features has one scale of variation and other features have different. And because of the different scales or ranges of values, the algorithm starts putting more. It pays more attention to one variable than other, while it should not be doing that. Should be paying equal attention to all of them. So for that reason, we do the min max scalar or the standard scalar.
Naveed, the other scalar was using the what do you call it? The deviation, right? The standard deviation.
Yeah, the mean and the standard deviation.
Is there specific cases when you'd want to use min max versus standard?
So I haven't looked into it, but Burhan, you can proceed and I'll comment on it in a
Okay,
while.
sure.
sure. So, although we had like the separate data for testing the data, but I wanted to see what the model could do if I split it in 80/20. So the random state is just because if you split the data without this, it would randomly split it, and then you would get different results every time. So I sort of like fixed it to get an idea, and then we actually constructed the model as you guys are already aware, and then we fit the values with X train and Y train, and then we predicted with the 20% that we left aside, and we got actually 0.79%, which is like 79%, which is pretty good for a logistic regression model. Yeah, that's what we did. Also, like, Navi, do you want me to go over the ones you did, like the XGB and random forest?
Yeah, so we haven't covered the theory of XGBoost and random forest and decision trees, and probably we wouldn't have time to go into them. But it would be a good exercise just to see if you would like to use them. That's how you can do it. Just a quick comment on these algorithms. So decision trees, XGBoost and random forest, both are called ensemble learning techniques. What they usually do is they make use of an algorithm called decision trees. So they combine multiple decision trees and then they take an ensemble of them. So the, the decision is made where the majority of the decision trees point toward a particular decision. So you just simply take the majority of them. The working of it is kind of a little bit involved, so we wouldn't go into that. But if you would like to make use of them, you can just simply import them from scikit-learn. For XGBoost, they have their own specific package called XGB or XGBoost. As you can see, we have imported the XGB classifier from XGBoost. So that's the library. You can just simply import them. And making use of it is pretty much similar to what you have been doing earlier, like with the linear regression or logistic regression. You declare its object and then call the fit method to train it, and then the predict method to make a prediction on it. XGB is a really wonderful algorithm. Like I've seen it winning lots of Kaggle competitions. Usually, they are sometimes used as an alternative to neural networks when you have limited data and you don't have lots of compute power. XGBoost can do a really good job in place of neural networks. So it's a very good algorithm to try whenever you are working with the tabular data like the one we are looking into right now.
Right. So yeah, it's fairly easy to use, but you have to like fit and then predict. So you guys could mess around with it if you guys want to. And then this is random forest classifier, which is just another technique, and we have used this as well. And then we got better results than before. So yeah, you guys could play around with it. So after checking, like I got 79%. I wanted to like test it on the testing data which was provided to us, and then I trained the model completely on like 100% on the training data, and then we actually prepared the data for the test CSV. It looks similar. Wait, I can show you guys the test data. But it's like literally the same as the training data. So there isn't much to see, but like you would do the same thing. You would encode the values. You would transform the data based on the missing values and stuff. And then once the data is ready, you could actually use it to predict. So I've used the testing data to predict, and then this is the results we got, right? And then I sort of like made an Excel that had all these entries that I later used to submit at Keiko. So yeah, that's pretty much it. And we got like wait, I'll share the Keiko score with you guys, but yeah, that's it.
Felix and Nishant, any questions from what you just saw?
I have
Yes.
one, but yeah, Nishan,
Oh no,
go
you can
ahead,
go.
go ahead first.
Oh, it's not really a
Okay.
question. It's more like a comment. But
Yeah.
what I noticed was even in my thing when I tried it on GPT 4.0, it was like saying that the accuracy was 81%, and then I looked everywhere for like the Titanic set, and everyone also got 80%. And what I found that was is if you train it on the model that the data was on, then you can only get like 98% plus. So like usually for the Titanic data set, it's the maximum it can get is like 80%. So I thought that was pretty cool. Just wanted to share.
Hmm, interesting. So what you mean to say is that
Burhan,
so what you
mhm.
mean to say is that like the maximum realistic accuracy is 80% with the data that they gave you?
Yeah, for the Titanic. That's what it says.
Hmm, okay, could be.
I was just wondering, Burhan, for the different methods, did you also get the same 79% accuracy, or was it more?
It was better because we used random forest and we got like wait,
Mm.
what did we get? We got 80%, 81% for the random forest, and
Okay,
for XGB we got 0.798, which is like zero point 0.6 more than what we got for the
better.
linear one.
Mm.
Mhm.
Hmm.
So I'm wondering, I don't know if this is possible, but I'm wondering, is it it should be possible to analyze like what predictors, what features are used to predict the outcome, right? And then at what importance, kind of level of importance. That would be something I would be interested in for this data set, but also in general, it would be cool to know like how does the model actually work internally.
Yeah.
Yeah. So yeah, I'll talk about that, the feature importance.
Okay.
Just a quick comment on the question James asked earlier. What's the significance between using a min-max scaler or a standard scaler? So the points that I've seen are kind of technical. I don't see a very intuitive
Right.
reason behind it, but usually we use min-max scaler when we know the bounds of our data. So like we know that it's a fixed region where the values would be coming from. So suppose if you have, let's say, an image, you know that the pixel value can vary between 0 to 55. So in places like these, we usually use min-max scaler um, because it is sensitive to outliers. We know that the values would be coming from a fixed region. There would be no outliers. That's why we make use of min-max scaler. It reduces the values between 0 and 1. Standard scaler is used when we are kind of um, somehow we know that the feature that we are using is normally distributed. The data distribution is normal. So what the standard scaler does is it reduces, it centers the data around 0,
Yeah.
and then it varies between some positive and some negative value. So if you know that the feature is kind of normally distributed, you make use of that. Generally, a normal advice would be if you are working with a data set like images or something, use min-max scaler. If you are working with problems like the Burhan was looking into or any other linear regression or logistic regression, make use of standard scaler. But there's no like, you can maybe use them alternatively as well. There won't be a significant impact on the outcome of the algorithm. Um, is Felix asked about the feature importance. It's a very interesting area of even research to look into the importance of various features that are contributing into the final decision. So for various algorithms, different strategies are used. For instance, if we talk about linear regression, um, we can have an idea about what features are important by looking at the coefficients of the features. So the coefficient which is larger, we can simply say that it is it is being paid most attention to, and if the coefficient or the weight is smaller, we see that it's not paying significant contribution to the final decision. But that thing is not very solid because it depends upon the the scale of the feature. So if the feature is varying, like if the range of the feature is very high, in that case, like it is dependent upon the range of the or the scale of the feature. So that's why there are other methods that are used in order to make sense of what features are important. So decision trees like XGBoost makes use of something which I don't like, haven't looked into its details, but it's making use of a there's a feature which I can quickly show you how to do that. For other algorithms like neural networks, since we don't have lots of visibility into how it's making its decisions, that's why there have been recent attempts to kind of interpret the model. There's a package or a technique called shape or shapey values, which are usually used.
Mhm.
There's another technique called lime. The technical details of it are, of course, it is being derived from what is called game theory or game theory approach. We can talk about it sometimes, but if we get some time, so you can make use of shape or lime in order to see how a complicated algorithm is making its decision. For simpler algorithms, linear regression, logistic regression, you can make use of the coefficients just to have an idea. And for XGBoost, they have their internal, they have this method built into their package, which can show you what features are important. I'll show that in a second. But before that, a quick comment about this
Naveed,
Titanic. Uh-huh.
could you just go back 1 minute and explain why, if the input data is normalized, why would the coefficients be affected by the range? Like, wouldn't the coefficients be then sufficient to know what's more important?
Yeah, so even if it is normalized, you can do that. So it can kind of give you a hint about what feature is important. Um, but still, I think it is usually it's not considered a very good approach, is because it is just simply taking the normal correlation of the feature. Like if it is increasing, um, it is just depending upon the normal correlation between the values. Sometimes normal correlation, which is something that Felix asked about earlier, like um, the correlation analysis that Burhan presented, it is just kind of giving you a limited picture of what's happening. The features could combine with each other in certain ways where normal correlations wouldn't give you the full picture, but if you combine them in intelligent ways, it can come up with something that is more useful. So maybe like even if you normalize it, it would be a simplistic approach towards um, deducing if a feature is important or not. But this is something that I haven't looked into in like a lot of detail, so I wouldn't be sure to comment much about it. But usually, it's not considered a good strategy to look into the features and decide if it is important just based on the weights of the values. You can do that for, let's say, linear regression, logistic regression, but how would you do that for complicated algorithm? That visibility is then lost. So that could be another reason why it's not very successfully used.
Yeah, I'm imagining, this is just what I'm thinking, but I'm imagining if you have multiple features that are very similar, then those will show up as being less important because they're all contributing um, to the um, to the output of the model. Do you know what I mean? If you have multiple features that are all correlated, they may be it may be hard to tell which of those are important. That's sort of what I'm thinking of.
I don't see that a very strong reason, because that's the whole point. If there are multiple features which are similar to each other,
Yeah.
And the weights are giving you like this, they're providing you the same values,
Mhm.
um, which would just simply means they are equally important. So I mean, it is telling you what it
Okay.
is. So
Okay.
it's not that reason, I
Okay.
think.
Got it.
Let me see. I think I had this notebook with me earlier, but I can't look at it right now. So let me do it once again.
Okay. Another thing is Nishant, would you also like to show us the solution that you came up with?
Yeah, sure.
Okay. I'll let Nishant do that. How's that?
Mhm.
Okay, cool. Yeah, show us your approach and what you came up with.
All right. So I use this to try and run it, and I pasted in the zip file, and then I was asking it questions on like the features that I would try and look for, and yeah, I also got the same accuracy rate as Burhan, which was 81% for when you use for the forest, which is pretty
So let's go
interesting.
through it step by step. What's the first step that it did for you?
Edit.
Oh,
It
okay. So
performed the
it's not
pre-processing,
everything in
and
one
then
step. It looks like.
yeah,
Can you click on that blue link that has like a little view analysis? Yeah, what does that do? Does that show?
That's kind of
JavaScript
the
code.
code interpreter.
Yeah.
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 Okay, interesting. So it's
It
extracted.
unzipped it and extracted it pretty much.
Has it done a regression?
Um,
Oh yeah,
it
there's
gave a
another one.
classification report, but not the
Did you see?
actual. Like when I tried to give the correlation matrix,
Hold
it
up. There's another code link. Did you see it? There's another
yeah,
code link. Oh, or is that the same one?
pre-processing.
That's the same one.
No,
Okay.
this is the pre-processing part.
Oh, okay. Okay. Sorry. So after, so what's so the classification report? How did it come up with this? How did it come up with the results of the logistic regression?
Um, all it did was literally just unzipped it, extracted it, and then it like unzipped the file so that it could read it, and then it was able to tell.
Felix, do you see where I'm confused? What does that code link do at the very end? View analysis. Okay, here it is. Got it. This is the one. So it's really important to understand how this code interpreter works. It generates text just like ChatGPT. It generates code, but then it also runs the code, gets the output of the code, and then passes the output of that back into itself, so that it
Yeah.
can generate more text. And we should at least have a good look at this code to see that it's doing something reasonable. Is there any way to make this bigger, or it just kind of gets this big? That's okay. We can kind of.
No, I don't.
Let's just scroll through it block by block, and let's see if we can understand what each block is doing. So, and yeah, feel free to chip in, Felix, as well. So
Yeah, so basically it's doing what also Burhan did, right? It's trying to close the gaps in the data
yeah,
here. I'm just thinking with age. Yeah, so it's taking the median age, okay. Embarked. So this one I think Burhan didn't do, right? Did you drop this one? Or did you also fill in
Nope.
the
I
the
only
missing data?
dropped like the Cabin one.
Yeah.
The thing I did was like a diff generally for all the float values. So I didn't do specifically the age and fare, but I did it together. So whatever float values were uh, missing in a particular column, it worked on it separately, but in the same line of code.
Hmm.
So that's what.
And,
Nice.
and it's also dropped the cabin here as well.
Yeah,
Oh yeah,
exactly. That's
I just
interesting.
noticed. Yeah.
Okay. All right. Did you also do that, Burhan, to convert the categorical variable?
Yep.
So here it's
Right.
here it's done it manually. It's instead of using the label encoder, but it looks like it should get this
Mm.
back.
What is it doing by the PD get dummies?
Yeah. Yeah, let's see, what is that? So it says get dummies columns equals bar. It says that this is converting the this is running the actual this is converting the embarked into can we scroll a little bit right? Drop first equals true. So it says converts categorical variable um, into dummy indicator variables. Okay. So it's converting strings. I think it's converting strings into
Okay.
numbers or into
Okay.
boolean true or false. Yeah.
Mhm.
Yeah, so the get dummies actually do one hot encoding, so it converts the categorical features into. So if you have, let's say, a feature, let's say gender, you have male and female. It takes that, creates two features out of it: gender male, gender female, and then assigns one in places. If the gender is male, it assigns one in the male column and zero in the female column, and vice versa if it's the other way around. So it's just encoding categorical features into numeric numbers.
Mm-hmm. Okay.
Mhm.
So
Okay.
okay. Wait, go back. Slow down. Go back up a little bit. Okay. So
I'm just curious because did you upload like the whole data set? I'm just wondering because it looks like if you go up a little bit, it says like it's splitting the data set, but we already had
mm,
two data sets, right? So it's splitting it further. I'm
yeah.
not sure.
Oh, because I'm pretty sure it's because like the file itself had different files inside of that file, right? So then it unzipped it,
Yeah.
and then
So,
I think it's evaluating it based on that.
so Burhan actually did this as well. He took the training data, and then within the training data, he split it into 80 and 20. But then after
Mm.
he tested his own model, his own process, he then went back, combined all the data, and then trained it final time.
Okay.
I'm pretty sure that ChatGPT did not do that. So then you'd be losing 20% of the data. Yeah, as you pointed out.
Hmm. Right, then it's normalizing the values,
Mm-hmm.
standardizing.
Yeah. Okay. And that's the same thing that we've done in our last class, and it's running the prediction, and it's doing that. Okay.
Is that it? Is there more below that?
There's more, yeah. But
I mean, in the code that that was it. Okay.
yeah, that was it. Yeah.
So Nishan, does that help to um,
Correlation.
does that sort of help to clarify a little bit, or
Yeah,
shine
yeah.
some light on what's going on when you're using ChatGPT for these kind of tasks?
Yeah, that was. I thought I didn't know the blue stuff was many courses, so I thought it was like a hyperlink or something, so I didn't click it. But
Yeah.
now I know.
Um,
Yeah.
so it seems like magic, but really it's doing the same thing that we're doing in Collab, but it's just hiding the code.
Yeah.
And I think it's not bad to use these tools, but I think you want to know what code works. You want to know what's the code that's working in case, sometime you actually want to do this, um, for a project of your own. Um, and you want to be able to make sure that if you need to debug something, that you know what code is doing what.
Hmm.
And so you can take this code and now you can copy and paste it into Colab as well, and you should be able to get the same results in uh, 5-10 minutes.
Yep.
Cool.
Okay, can I share my screen?
Yes.
Okay, I couldn't get the Titanic dataset, so I did this quickly on the cancer run.
Okay.
Um, so it's pretty standard loading the data, then encoding the diagnosis column because it's a character, malignant and benign. We just simply convert it into the 0 and 1. Even if you don't do that, scikit-learn kind of takes care of that, but just know that this is something you have to do. If even scikit-learn is, if you don't do it, scikit-learn is doing it internally. We have the features and the labels, and then we do the trend split. So a normal practice would be to split the data before doing the standardization. The logic for this is if you train your algorithm, the data set that you trained it on is with you. So when you do the, let's say, the normalization, you know the mean and the standard deviation of the data because you have it. Um, but if you are testing this on a data, like the goal is to make use of this model on unseen data. For unseen data, you don't have that mean and standard deviation. The hope is that the distribution of the data stays the same even if you don't have it, like the overall trend stays the same. But just to be sure, you don't do the standardization before the trend is split, just to make sure that the test data that I'm going to test this algorithm on is not, it's not having the knowledge of its mean and standard deviation. So what we do is we first split it, we then do the standard scalar on the training data set, and we make use of the same scalar to normalize the test set. Now the information this scalar is having about the mean and standard deviation is not about the test set. It is, that information comes from the training set which it has seen, and we make use of that to normalize the data, the test data. Does this make sense?
Yeah.
Perfect. So making use of XGBoost is super simple. We just simply import it. There's a separate package for it. Scikit-learn unfortunately doesn't have it. The reason for it is there were this concept is called boosting trees. Now there are um, multiple strategies people utilized in order to make use of the boosting trees algorithm. XGBoost is one variant of it. That's why, like, because of the wide variety of ways you can combine decision trees together, there are multiple variants of the boosting trees algorithm. XGBoost is one of it, and the package that contains it is XGBoost, so you have to import it and make use of it. Um, but simply we just declare the classifier object and then train it, and then make use of its predict method and do the prediction. The score is 96, which is a pretty high score. You'll see when we'll make use of neural networks to solve this problem of the cancer run, the score would be very close to this. And we have the confusion metrics. You know these things, right? The confusion metrics and the precision recall and the font score, these metrics.
So we've definitely gone through the confusion matrix, which has the false positives and the false negatives, and the true positives and the true negatives. I don't think we've really gone through each score.
Okay.
Yeah, can you
These
the last score? I didn't get it. Support or
Okay,
Yeah,
this is not a evaluation metric. This one just shows how many examples it was evaluated on. So it just shows the number of benign cases that you had in your data and number of malignant cases that you had in your data. And do you want me to talk about these three?
sure.
Okay, so usually for classification tasks, accuracy provides a good measure of how the algorithm is performing. The accuracy is just simply taking the correct classifications and dividing it by the total number of examples that you have tested your model on. So in the support column, if you see here, we have a total of 114 examples. This score of 96 is evaluated based on those. Why would accuracy not be like in what places it could not be a good measure? It could not be a good measure in places where we have skewed classes, where we have lots of examples of one class and fewer examples of another class. In that case, accuracy can kind of deceive you. A quick example would be if you, let's say, have a test data where, let's say, 98% or 98 of the, like in total there are 100 examples, 98 of them were, let's say, benign, and just two of them were malignant. And you have, let's say, a training algorithm, an algorithm which is trained, and um, let's say we know that this algorithm is doing nothing but just simply predicting for whatever example that we are feeding it, it is predicting that it's not a malignant tumor, it's a benign tumor. So all the time it's just simply spitting out benign, benign. If we pass this 100 examples from this algorithm, for 100 of them, it would say it's a benign case. If we want to now evaluate the performance of this algorithm, we can make use of accuracy. Accuracy is correct classification divided by total number of examples. Um, Out of 100, 98 of them would be correct classifications because 98 of them were benign cases, and the algorithm was just predicting it's a benign case. So the accuracy would turn out to be 98%, which seems a very high accuracy. It can deceive you into thinking that the algorithm is performing really a good thing, a good performance. But we know that it's not doing that. It's just simply spitting out that it's a benign case. So that's how accuracy can kind of deceive you in these places. And that's where these precision, recall, and F1 score, which is just the combination of these two, it becomes handy. So if you quickly look at the formula for precision, you'll see it is making use of these concept called true positives and false positive. What is a true positive? If an algorithm predicts that it's a positive case is usually, for this example, a positive class would be the malignant class, so it's usually considered the positive class. If you are testing for something and the presence of that thing is usually considered as a positive class, you can do it the other way around as well, but usually that's how it's done. So the so if we want to evaluate the precision score, so true positives, what it is when the algorithm predicts that it's a positive case, and the ground truth is also a positive class. In other words, a correct classification. That's a true positive. What's a false positive? If the algorithm says it's a positive class, like it's a malignant class, but in ground truth it's not a positive class, it is a benign case, that then turns out to be a false positive. Does this make sense?
Yeah.
Felix, Nishant.
Yep.
Okay, so let's see what will be the precision score of an algorithm that I was talking about earlier. That's just spitting out a benign for every case. So how much would be true positives there? There would be zero, because all the time it's saying it's a negative class, it's a benign class. All the time. For 100 of the examples, it's saying it's a benign class. So precision turns out to be zero. It correctly identifies that flaw in our model, that it is all the time is just simply spitting out it's a benign case. You see the importance of precision now?
Mm-hmm.
And recall is
Kind of.
kind of, okay, I know I'm just quickly talking about it without explaining it on the whiteboard. Maybe I'll do that in a future session sometime. But it's kind of picking those kind of limitations in
Yeah.
our models where accuracy would kind of wouldn't be able to see it directly.
So
Um,
I found it a bit confusing as well when I was looking at the equations.
uh-huh.
Um, So I sort of wrote down these common explanations that sort of made sense to me. So accuracy is overall how often is the classifier correct in its prediction. Okay. Precision is when the classifier predicts a positive value, how often was that prediction correct? Only when it predicts a positive value. And then recall is when the prediction was supposed to be positive, so when the actual value is positive, how often did the classifier get that? Does that help? Does that way of explaining it help at all?
Yeah, so for precision,
Yeah.
it is doing it is testing the ability of the model of recognizing a positive class, how much this algorithm is able to identify a positive class, while accuracy wouldn't be able to do that. Accuracy is just simply looking into if the decision is correct or not correct. It's not testing a specific class for you. It's not testing the accuracy of the model for the positive class. It is overall general accuracy of how much the model is doing making correct predictions. Now, if an algorithm is continuously predicting a negative class, the accuracy is 98%, but the precision is zero because it's not even for a single case, it's not saying it's a positive class. For all the examples, it's saying it's a negative class. So it is missing on the ability of the model to identify the correct classes, right? I'll talk about this in detail. Let me just quickly show you what I was actually doing this code for. Um, yeah, so I was trying to show you the different methods that you can use to identify the importance of the of various features. For some reason, it is not showing the names of the features here. So for XGBoost, it's internal plot importance, um, internal mechanism of identifying what is a which which feature is more important. That's how you can do it. It has this method by the name of plot importance. You can pass in your model, and then there are multiple ways it can try to identify which features are important. Um, Gain is one of the the technique. What is gain? Again, it's specifically um, it is something that the XGBoost, the way it makes its decisions. I know it won't make any sense to you right now because we haven't talked about it, but just for the coding sake, that's how you can um, see which feature is important. So if the feature with the highest F score just simply means this feature is more important. And this is not doing something simple like just simply telling you the coefficient of the of the features, like the one I was talking about earlier. So coefficient analysis would just simply tell normal linear correspondence between features. If the algorithm becomes complex, like in XGBoost or neural network or any other complicated algorithm, you cannot make use of the simple um,
Mhm.
coefficient analysis in that place. So that's why we for XGBoost they have their own way of evaluating the importance of the features. But for other algorithms, like there's a generic package which you can make use of in neural networks for XGBoost as well. For any kind of model, that they do this for all of it. The internal working, again, it's derived from an approach called in game theory. I once looked into it. It's a detailed analysis. If we get sometime, if we get time, sometimes I'll talk about it in detail. But the way you do it is just simply Colab doesn't have this package in advance. You have to install it using pip, and then you just simply pass your model um, to the shape explainer object and the training set that you have trained this model on, and then it evaluates what are called the shape values, and then you can plot various types of plots for them. So if you go to the GitHub repository of the shape, they have like a really wide variety of plots explaining in different ways how the model is making decisions, what features are contributing the most. The simplest one is the summary plot, which just simply gives this. bar plot telling you which feature is mostly contributing and which is less contributing. So here it is saying area worst, and these features are contributing the most. Now if you compare it with, I think I don't have the correlation analysis here, but if you compare it with the ones for the correlation analysis, there the correlation was something different there, like the feature was different, but the shape is now telling us that this feature is important one. So correlation analysis just simply looks into the linear correspondence of the features, while shape or other explainers like the XGBoost one then goes one step further, and it also then looks into how features are interacting with each other, and like in the long term or in the final stage, what which features when combined in certain ways is then contributing the most. So it's not just simple linear correspondence, it is something that is deeply dependent upon the way the model is making its decisions.
So the way I
Nice.
understand, I don't really understand how it works, but Shapley values is sort of trying the model with and without certain features to figure out which features are more have the strong.
Exactly. Y- yeah, so I haven't talked a bit about how it works. That's why you don't understand it, but it's just a way how to evaluate the model.
Okay.
Sorry, how to interpret or how to figure out what features are contributing the most into model decision making. Now if I, like, we can do that, I can talk about in detail how shape values are computed, but as you know, we wouldn't have time for the rest of the interesting stuff that we have planned.
And we're just about out of time for today as well.
Hmm.
But
Nice.
oh,
Thanks, Navid.
thanks
Right.
thanks Naveed, and I want to thank our star for today, Burhan. Thank you very much for joining us.
You're welcome.
And um, yeah, we may change around the schedule possibly. But before we do, I'll make sure to check individually with everyone that it's actually better for them. Uh, so I will be in contact with you directly. Don't worry. Cool. And but other than that, our next session is on Thursday, and we have my favorite topic, which is we're going to go over how neural networks work.
Thanks,
Cool.
James.
Yeah.
Sounds
Thanks
good.
everyone.
Thank you,
See you
James.
Thursday.
And
James,
Naveed.
just give me a minute
Yeah, sure.
after this. All right.